start back by saying once again, I made a summary of our discussion on the generation of synthetic data, and basically I want to say that I focused on the generation of the data, and I'm not focusing specifically, with the exception of some small topics, on the procedures for water resources management. So I stop on the hydrological part, because procedures are discussed by Elena Toth in her course, and I want to avoid overlaps. So I provided to you the tools, the main tools for the generation of synthetic data, rainfall modeling or hydrological modeling in general by using deterministic approaches, and the stochastic generation. And for the stochastic generation in particular, I made an attempt to propose to you a new approach to studying the problem. So if you have any questions, any doubt, please let me know. And what I want to tell you is that this approach that I adopted is highly technical. So as you said, we had the opportunity of making an experiment of actually generating data, actually with quite good results. And keep in mind that this is an exercise that usually is considered to be quite complex. And in order to quickly get to the results, I introduced to you only the essential part of the theory. And this is something that you have to take into account. Basically, from a technical point of view, you don't really need what I didn't discuss with you. You don't really need to know what are implicit assumptions that are embedded in this approach, which again I didn't discuss with you because they are quite technical. You don't really need it because from a technical point of view, it's more important that you check the results. It's extremely important, as I said, that you make a lot of checks. And in particular, once that you generated the series, it's necessary, as I already told you, that you check that the behaviors you are much interested in are well reproduced. So if you're interested in floods, check the extremes, how they look in the synthetic series, if they are comparable. I mean technically comparable to the data that you have and your expectation. Technically comparable means that the order of magnitude is fine, means that for the purpose of what you are required to do, it's the generation, it's reliable according to your perception. And this is what is important. On the other hand, I want to make clear that in the future, if you decide to take a PhD or a master, and you decide to make research activity on stochastic processes, I want to tell you that there are important parts of the theory which I didn't discuss. And these important parts are essentially statistical and are implicit assumption that you are required to check in order to make sure that your estimated parameters are consistent, in order to check from the side of the theory that everything is going fine. I focused on the side of the application, and therefore I recommended to you, look at the data, check that from your application they are fine. But there is another possibility to check the reliability of a simulation of a model, which is to check if the underlying assumptions and theory are fully satisfied. There are some people, in particular researchers, they say once that assumptions are checked, once that the model is checked, the simulation is by definition reliable. So you don't have the tool for doing that. In my opinion, this is not really true. I think that we should make sure that the theory, the assumptions are respected, but on the other hand, we have to perform the technical check. I focus on the technical check, not on the theoretical check. So there are some checks that you don't know. And again, they refer to the theory. And I just wanted to make it clear, because this approach that I adopted, I think it has the advantage of being, in my, hopefully, in my will, it's more appealing because it focuses on the application. On the other hand, you know, it's quick and therefore it's missing some details. So I think that we can close this, and the next topic I want to discuss with you is drought. Let me start again from the application. Drought management. Did you discuss drought management with Elena Toth? Did she speak about droughts, how to cope with droughts, what are the techniques for doing that? Probably not.
No.
Okay.
Sorry?
Sorry?
How to identify by
Identify. So monitoring, and did she speak about drought indexes?
Yeah.
Okay, so you know something.
But can I add something? Some people are from the other program, from the
Yeah, I know.
so we don't have.
Yeah, I know, but I, you know, I want to try to avoid the overlaps, and therefore I can adjust a bit. I mean, I will speak nevertheless of drought indexes, but very briefly. Okay, and okay, this is fine. Did she speak about drought prediction? I don't think so. Okay, this is perfect. And so the application from which we start is drought management. So procedures for coping with droughts. I will make just a brief mention to the procedures because, again, I'm not interested really in the design. I'm interested on the hydrology part. So what I want to discuss with you is how to monitor droughts, and in particular, I wanted to explain to you a tool that is still debated by researchers and focused on by researchers, which is drought prediction. And because it is extremely important in order to cope with drought to be able to predict that. So, first of all, droughts are an extreme hydrological event, like floods. They have something in common with floods, because, for instance, you can study the frequency of droughts by using the same models that you use for studying the frequency of floods. So you can estimate, if you consider drought as an extreme value, so if you associate to droughts a given random variable, which can be, for instance, the annual minimum of something, annual minimum of river flow, annual minimum of rainfall. If you do that, so you associate to the event, drought, a random variable, then you can study this random variable by using the theory of extremes in the same way as you did for floods. So let's suppose that you want to know what is the frequency of the annual minima for the Po River. You just have to take the series of the annual minima and treat this series as a series of extreme events, and you can estimate the lowest flow for a given latent period, which is not really something that gives the idea and the intensity of a drought, because I will speak to you later why. The flood is almost fully identified by the peak flow, but on the other hand, I told you that in some cases it's extremely important to determine also the flood hydrograph, which is the shape of the event. For floods, it's not really extremely important. I told you for the design of some of the infrastructure, it's important, the flood hydrograph. But in most cases, we just need the peak. For droughts, and this is a first difference, the only value of the minimum flow is not enough in most of the cases, because, you know, this is a point value, and the main difference between one first, I would say that it's the main difference between floods and droughts is that floods are typically a quick event, while the drought is long-lasting. If it is not long-lasting, it's not really a drought, because the problem with droughts is their duration more than the magnitude of more than their magnitude. So for this reason, usually it gives to you a scarce information, the only value of the minimum flow of the Po River. It's more important that you know the duration of this event. But on the other hand, if you are interested in studying the minimum, for instance, because you know, you may be interested in the minimum because you want to design the level from which in the river you displace water intake. And therefore, you may be interested in knowing what is the minimum water level with a given frequency of occurrence. So if this is your problem, you can estimate the frequency, as I said, of the minimum as you estimate the frequency of the maximum. Keep in mind that usually the probability distribution is different. So while you use the gamble for fitting the maximum, because it usually provides a good fit, if you make an attempt to fit the gamble to the minima, usually it doesn't provide a good fit. So you have to select another probability distribution. I'm not focusing on the details because, as I said, it's not really important from a technical point of view. What is important is to also estimate the duration. And also there is a second difference between droughts and floods. The floods are usually localized in space. The droughts usually hit a large region. Sometimes it may happen that also floods occur in clusters, but usually the event flood refers to a place. And the place can be extended, but not much really. If you look at the flooded areas, usually they are very, confined. Of course, they may interest a full city, like Florence in 1966, but it's still only one city. If you think at the big drought that occurred in Europe in 2003, it was extended over the whole Europe. And usually a drought is at least extended over the extension of a country or a part of a country, because otherwise it's not really concerning. And also, the drought is a meteorological event. It's not an event originated by a river. So meteorology is, of course, a much more extended process. And this makes the relevance of droughts really important. Usually, if you look at the hydrological events that caused and are causing the highest number of deaths, then you find the floods in the first place. But if you look at the events that caused the higher damages, it's quite frequent that droughts cause and higher economical damage because, as I said, they are extended and their effect is therefore extremely important. In order to cope with droughts, as I said, there are a lot of interventions that can be set up, but in order to effectively plan these interventions, we need to know, for instance, the intensity of the drought that is occurring. So given that a drought is occurring, it's extremely important that we quantify it. And it's not easy. I will explain to you later why. It's really not easy. First of all, because we have several types of droughts. So we have to fully identify it. Identify what is the type of the drought, and then to identify the magnitude. Second, it would be extremely important to effectively plan the droughts to be able to forecast them. And forecasting means forecasting is always associated with time, and for effectively cope with the droughts, we would need a forecasting with some months in advance. And this could be in principle possible because given that the drought is caused by a slowly evolving process, it's not like floods that may be caused by something that happens suddenly, even that they are in general generated by large-scale patterns, it could be in principle possible to predict them. And a drought prediction would allow to make important step forwards in terms of effectiveness of our action to mitigate droughts. Because of course, if you could foresee a drought, then you can increase the available water storage. If you have some months in advance to plan, of course, this allows to make the action much more efficient. So, first of all, let me focus on monitoring, and not much, as I said, because I suspected that I already focused a bit. And first of all, let me say that in many nations, if you focus on drought, if you Google, first of all, let me say I forgot to tell you at the beginning, I still don't have a lecture in my homepage on this, but I promise during the weekend or at the latest by Monday, Tuesday to get, to get online. I still need to complete the part on stochastic simulation. It's almost completed, but I still need to work a bit on it. And then I will provide to you the page with all the links. So first of all, if you look at Wikipedia, you find the definition of the drought. And then I give you some links to follow. First of all, before I move forward, let's define what is the drought and what are the types of droughts that we need to know. And first, the drought, as you see here, is a period where we have a below average availability of water. And it's important that you distinguish drought from water scarcity. They are two different phenomena. Water scarcity means a perennial reduced availability of water. I mean, a perennial deficit of water availability with respect to water requirements. So there are some countries which experience water scarcity. It means that they don't have enough water forever to satisfy all the requirements. And this is a different thing. The drought is instead something that is temporary. And a drought can hit, of course, both water scarcity areas and areas that in normal condition do have enough water. So for instance, if you think of Italy, Italy is a country where we don't experience water scarcity for most of the part of Italy. So with the exception of some of the islands and some limited part in the south, Italy is not experiencing water scarcity, but it's subjected to droughts, which occur quite frequently, with an higher frequency in the south for reason of geographical location, different climate. And therefore it's extremely important that we distinguish. So what is a drought? Again, it's a period of below average water availability. Here there is written below average precipitation. This is a limiting definition. I would say, to make it more general, it's a period with below average water availability. And in fact, we can distinguish between, as I said, several types of droughts. So we may have the meteorological drought, which is a period of below average precipitation. So this definition here, I would say that it's a definition for meteorological drought. So if you have below average precipitation, you have a meteorological drought, but population may not suffer, because if there are enough storage, people don't suffer. When you open your tap, still you get water, even if you are in a period characterized by a meteorological drought. And also keep in mind that the meteorological drought implies that, of course, you have a period with no rainfall. But if our main water source is groundwater, we don't suffer at all. So indeed there is a meteorological drought, but from the point of view of the civil use, we don't suffer at all. Maybe that the agriculture suffers. In fact, a second drought is defined as the agricultural drought. It means that we have a period with below average water availability for agriculture, which can be extremely important. Even if the civil use is not impacted, you know, the agricultural drought is still extremely important. And then another type of drought, which we may define, is the hydrological drought. And it's defined as below average surface water availability. So if you have a reduced storage in reservoirs, if you have below average water flows in the rivers, we say that it's an hydrological drought. I would say that we can, sorry, let me also introduce, because I would say that, you know, the hydrological drought usually doesn't include a below average availability of groundwater resources. And the reason is that, you know, the timing of the two phenomena is extremely different. So to associate these two phenomena, it wouldn't be a good idea. Because, you know, hydrological drought, one could consider a shortage of all the water sources for a given domain. But indeed, we usually make a difference between the surface water and the groundwater availability. So hydrological drought is defined as a below average surface water availability. And then we can speak about a groundwater drought, which means below average groundwater availability. And these two phenomena, as I said, are not associated because they have a different time scale. The recharge time of groundwater resources is usually extended over the years. It may take years to replenish a groundwater reservoir, while it usually takes no more than a couple of weeks to replenish river flow, and also, you know, to recover the storage in reservoirs doesn't take so much as recovering the storage in groundwater. So we spoke about drought in general, reduced water availability, agricultural drought, hydrological drought, groundwater drought, and you may extend it. If you refer to particular context, you may extend. In general, the idea is that we have below average water resources availability. This is the definition. And of course, when I say below average, it means that I have to refer to a period. And in fact, usually, as I said, the drought is not measured by referring to a point value. It is measured by referring to an average value over a period, as we will see. And some of you already know, because some of you already know how to monitor the droughts. Okay, and therefore in this page you can see also some more details, and some of them we will discuss during this lecture. Okay, so let me now focus on drought monitoring. And if you Google drought monitoring, you get as the first link the United States Drought Monitor. And this is an example of a monitoring service for droughts. And what you see here is the current situation. And the current situation where the yellow, if you look at the legend here, the yellow means abnormally dry. The light brown means moderate drought, and the darker colors means exceptional drought. So basically, abnormally dry is the first level of warning. And then we go down to the darker colors with the 4 meaning exceptional drought. And you see that for most of the United States it's white, which means no warning. And it would be interesting to see what is here the monitoring variable, because it doesn't tell you what is the variable that allows them to make this classification. And let me see if it is specified, because I just clicked on the link and let me see. Probably there is statistics comparison. this is in terms of percent area. So here you see it's these are statistics that allow you to make an estimate, a comparison with the previous period. So basically you see that now there is in the yellow condition, or let's look at none. Currently we have none percentage of 70% of the area which is not affected by drought. And if you look in the past, you see that this is quite a good situation, because only in one case they got 3 months ago, up to 1 year ago, of course, they got higher percentage. And also there are here the condition for the contiguous United States, and this is in terms of percentage area. And but they still don't say here how it's computed, and this is extended to other periods, longer periods. And let me see, change maps. So let me see, I think this is basically, one can change the map here, and in particular, it's one can change the period. So basically here there is a variable that is averaged over a period, and I'll tell you according to my guess what the variable is. But in any case, as I said, it's important to specify the duration, and here one can change the duration on which this map is downloaded, is depicted, and then can be downloaded. Okay, supplementary info, current conditions, let me see, this is still. Okay, here for sure there are the details, but let me focus now on another website. You will see that if we go back, here there is a map archive, and here you see there is already the link to a climate prediction center. And then I think if we browse down, of course the United States have a drought service that is very, very experienced and already run for a long time, and therefore they occupy all the links, all the first links in the page. But you see here there is an African flood and drought monitor, and etc. So basically what these services do, they provide online and real-time estimate of the drought condition. Now, how can we quantify the intensity of a drought? And very briefly, it is done by using drought indexes, which I will provide the link to the computation. Unfortunately, it's not easy to find a link. I struggled to find a link with a clear explanation in mathematical terms, and I couldn't find it. So I need to develop something myself. And because there are always written descriptions on the web page on how the indexes are computed, but I couldn't find any, up to now, any satisfactory analytical description. The reason basically is that when you write web pages, as you may know, to write text is extremely easy. To write formulas, it's more complicated and takes a lot of time more. So this is the main reason why people in the web page usually, it's difficult to find formulas. You usually find them in the PDF, but it's difficult to find them in the web pages because they require some advanced manipulation. So basically, how can we monitor the drought? There are drought indexes, as I said, and the simplest one is the computation of the deciles, the so-called deciles. And how can we do that? First of all, we have to select a variable. And let's suppose that we refer to precipitation, but the variable could be river flow, or could be water storage in a reservoir, whatever is relevant to you. I mean, once that you define what is the type of drought that is relevant to you, like a drought in a water supply system, you identify that the water supply system is fed by a river, and then you get to the definition of the variable which is relevant to you, which is the river flow. And then the idea is to select also not only the variable, so one first step you have to select the variable that is to be monitored. In most of the cases it's precipitation. I'm quite sure that in the map of the United States that I showed you before, it's precipitation the variable. And then the second step is to identify the duration which is relevant to you. And as you saw in the maps that I showed you before, the duration was your choice. They allowed you to choose the duration. And then what you have to do is, third step, compute the mean value of the selected variable over the given duration. So you compute the average, like if you decide that the duration is 1 month and the variable is precipitation, what these maps do, they compute the average precipitation in the last month. Okay? And then you have to compute the long-term average. What does this mean? What does this mean? If the program, the algorithm is sophisticated and you basically you make your query today and you select 1 month, what the algorithm does is to compute the average precipitation in the last month, and the last month is from May 13 to April 13. And then the algorithm looks back in the historical record of precipitation and compute the long-term average in the same period. So if the algorithm has daily precipitation available, it computes the long-term average from May 13 to April 13. So you can compare the average in the last 30 days with the long-term one. And basically what it is computed is, let's suppose that the average in the last 30 days is indicated with the symbol precipitation over the duration d, and with an over bar, which means average in the last month, you divide it by the same precipitation d long-term average. Let me identify with 2 over bars the long-term average. So you compare the long-term average with the average that is experiencing now. And then this value is multiplied by 100. So if this value is, the result is 100, it means that you are in normal conditions. And the result, usually, is divided in classes which are called deciles from 0, 10, and this is the first. And the last one, the 10th class, is from 90 to 100. And these are called the deciles. And what we say is that if you are in the 10th decile, you are in normal conditions. If you are in the first decile, you are in the worst condition with regard to drought. And usually they assign different colors to the deciles. This is, in my opinion, how these graphs, these maps that I showed you are computed. But of course, if you're interested, look at the website for more details, because there are other drought indexes that are computed. As you see, from a conceptual point of view, there is nothing here. It's trivial. It's trivial. And this is also why droughts are often not taught in the university courses. So we usually teach how to cope with floods, how to estimate extreme floods, how to estimate water resources availability, but usually in the classical courses we don't teach how to quantify droughts because, you know, it's extremely simple. And you will see that the other indexes are a bit more complicated, but they are all simple. Of course, you have to remember, because, you know, even simple things need to be remembered. And this is something that they can ask you at the exam, and I consider this a very easy question to reply. So if I ask you drought indexes, you will see that also the other indexes are very simple. Okay, and I just want to mention another one, because then I don't want to give more details because I don't want to overlap. Because the second one, which I'm now mentioning, it's more used. So I think that maps of the United States surface probably use this second one, not the size. But it's very similar because the kind of variables that you consider, it's the same. So let me talk about the second one, which is called, the standardized precipitation index. And I'm quite sure that Elna also mentioned it. Standardized precipitation index also